Hi, and welcome to this talk on sinusoidal carrier modulation. Here's an overview of this lesson. Sinusoidal carrier modulation, which I will refer to using the acronym SCM, is a way to send information using electromagnetic waves. In fact, it is, by far, the most common way to do this. Systems that use SCM include communications, including for sure cellular telecommunications, radar, telemetry, radio frequency identification, RFID, global navigation satellite systems, including GPS, and the list goes on and on. In this talk, we'll define SCM and explain why it is so common. SCM comprises many specific modulations, but these can be sorted into one of two categories, namely analog or digital, so we'll make that distinction. Within each category, we'll briefly identify a few specific types of SCM. This will be just barely scratching the surface, but it will give you a feeling as to what the possibilities are. In this lesson, we'll begin to talk about the concept of bandwidth. Of course, if you're interested in communication systems design or spectrum management, bandwidth is of paramount importance. Here we'll begin to address the issue, although we will not yet be ready to say exactly how different forms of SCM compare in terms of bandwidth. That will have to wait for another lesson. Here, first, we just want to get you familiar with what it means to be a sinusoidal carrier modulation. So, here is SCM. The expression describes a sinusoid. That's it. Just like any sinusoid, it has a magnitude, that's capital A, and it has a frequency, that's little f, and it has a phase, that's phi. And you choose values for A and F and phi, and then you have a sinusoid. So you might think of A and F and phi as knobs that can be turned to select a particular sinusoid. What makes this a modulation is that A, F, and phi are varied to represent information. Which combinations of A, F, and phi are varied, and precisely how, this is what defines the modulation. So the idea is you convey information by turning the knobs. For example, if you want to send the sound of your voice, you might use the voltage from the microphone to vary the magnitude A. Then A of t is the voice waveform, and you have what we call amplitude modulation. Now, we could also use the voice waveform to vary F or phi, and we do. This would be frequency modulation or phase modulation, respectively. Now, one small caveat about that. Although we often like to think about frequency and phase as being independent, that's not exactly true. In fact, frequency is the rate of change of the entire argument of the cosine function, and it's not just f. So, phase modulation is also a form of frequency modulation. Nevertheless, it's useful to think of control of f and control of phi as being two separate possibilities leading to two separate modulations. If for whatever reason you're not sending information, then you're not turning the knobs, and so A, F, and phi remain constant. For example, this happens in frequency modulation when you stop talking. Then the frequency stops changing, and you have an unchanging sinusoid. In this case, we have what we call a carrier. Since the carrier is a sinusoid with constant amplitude, modulation, and phase, it has zero bandwidth. What we mean by this is that all the power is packed into a single frequency, namely the unchanging frequency f. However, once you start turning the knobs again, there is information, and subsequently the bandwidth will become non-zero again. In fact, one finds that the bandwidth, that is, this amount of spectrum occupied by the signal, increases in proportion to the rate at which you turn the knobs. In other words, bandwidth is proportional to the rate of information. There are many waveforms that you could imagine using to send information in lieu of sinusoids. For example, you might consider doing this with square waves or sawtooth waves. There are infinite possibilities. But there are two things about sinusoids that make SCM the most popular method. First, it's really easy to make nice, clean sinusoids at radio frequencies. In contrast, virtually any other periodic waveform is more difficult to generate. Second, SEM facilitates modulations with very low bandwidth. You got a taste for this idea from the discussion of carriers on the previous slide. Any other choice of carrier waveform results in a signal having greater bandwidth, which is undesirable from both an engineering and a spectrum management perspective. Now, just to be fair, let me point out that there are useful alternatives to SCM. For example, you might consider sending information using combinations of very short pulses. This is called pulse modulation. Specific forms of pulse modulation include pulse position modulation, which you might know by its acronym, PPM, and also impulse modulation, which is sometimes known as ultra-wideband modulation, or as it's sometimes known by its acronym, UWB. Now, PPM, UWB, and other forms of pulse modulation are used in some systems where their advantages outweigh their disadvantages. So, what disadvantages, you might ask? Well, as I mentioned earlier, it's harder to make precise pulses than it is to make precise sinusoids. Also, all forms of pulse modulation have relatively large bandwidth relative to the rate of information. And pulse modulation tends to generate harmonics, which are copies of the signal at integer multiples of the desired frequency and or multiples of the rate of information. Suffice it to say, pulse modulation is not very common. So, we return to SEM and we want to make an important distinction. That is, the difference between analog and digital modulations. SEM can be either one. Analog modulation means that the information is continuously varying, and so is conveyed by continuously turning the knobs for amplitude, frequency, and phase. For example, the way we send information is by varying the amplitude according to the volume of our voice. Then we have amplitude modulation, or simply AM. If, on the other hand, we vary the frequency in proportion to the volume of our voice, then we have frequency modulation, abbreviated FM. The hallmark of a digital modulation is that information is sent in discrete chunks. These chunks are called symbols. An important type of symbol, and one you surely already know about, is the bit, which is a symbol consisting of two states. Now, people like to say that the two states of a bit are 0 and 1, but in fact, all that really matters is that there are only two states, and you can label them however you want. A key idea is that in a digital modulation, symbols map one-to-one with states of the carrier. That is, each symbol corresponds to a particular set of values for amplitude, frequency, and phase. For example, one form of digital modulation is to keep frequency and phase constant, and then to set amplitude to either 0 or a non-zero value, depending on which bit you care to send. This particular digital modulation is known as on-off keying, which is abbreviated OOK, sometimes, perhaps commonly pronounced ook. Now, ook sounds a lot like AM, but it is not AM. In ook, the carrier can have only one of two possible amplitudes, and furthermore, it changes only at specified times, whereas in AM, the amplitude continuously changes. Now, you may wonder why we bother with digital modulation. The first answer would be, of course, that some information is inherently digital. For example, if you want to send a data file, you are essentially sending bits anyway. Well, this is true, but it doesn't really answer the question of why we might want to send a voice signal, which is intrinsically analog, using digital modulation. In other words, why go to the trouble of digitizing voice and then using ook, when you could just send voice as AM? The answer to that question lies in the finite alphabet property of digital modulation. Finite alphabet means simply that we know that at any given time there is only one particular symbol being sent, and we know that the symbol is one of a small number of possibilities, perhaps as few as two possibilities, as in the case of ook. When we receive ook, we're making decisions between those two possibilities. Each decision will be either correct or incorrect. If the signal-noise ratio is high, then it will almost always be correct, and so we will have received this signal with essentially perfect fidelity. Now, this never happens in an analog modulation. In analog modulation, the noise always degrades the information, however slightly. But where digital modulation really shines is at the lower signal-noise ratios. In this case, analog modulations produce really poor fidelity. Anyone who's ever tried to listen to a weak AM or FM broadcast radio signal can attest to this. However, what happens when digital modulation is used in the same scenario is simply that you make more incorrect choices. For example, in ook, the rate of bit errors goes up. But this is a very manageable problem because there are lots of schemes that we can use to detect and correct these bit errors. Using one of these error control schemes, we can get back to the condition that nearly all of the bits will be correct, even when the signal is received in very low signal-noise ratios, where many of the initial decisions might be wrong. This is where the finite alphabet property of digital modulation really pays off. There is simply no analogous form of error correction for analog modulation, so this accounts for much of the preference for digital communications in modern radio systems. Okay, now let's talk about some specific analog sinusoidal carrier modulations. And to be clear, analog modulation is still in common use, although mainly for historical reasons. That is, analog modulation is used mostly by systems that became established in the early and mid part of the 20th century before digital modulations became practical. In this table, I'm showing just a few of the important analog modulation schemes. To begin, let's talk about amplitude modulation, and a rather specific form of amplitude modulation known as double-sideband large carrier modulation, typically abbreviated DSB-LC. The best known case of DSB-LC is broadcast AM, which are those broadcast signals around 1 megahertz that you can still receive on most car radios. Another important use of DSB-LC is in aviation, for communications between aircraft and the ground in the VHF band. There are a handful of other uses, but those are probably the two big ones. The way you make DSB-LC is to simply vary the amplitude of the carrier according to the amplitude of the audio signal. So in the figure on the lower left, the top curve is the audio signal and the bottom curve is the modulated carrier, and that's what goes out over the air. One thing to note is that you can see in this figure that the carrier magnitude is never reduced to 0. And that's what makes it large carrier AM. The carrier is always present, even if the audio signal goes to 0. And there are two things you should know about DSB-LC. First, as I pointed out, there's a lot of power in the carrier. And since the carrier contains no information, DSB-LC invests a lot of power on a part of the waveform that conveys no information. Now, you might wonder why anyone would put up with that. Well, one reason is because that always present carrier makes this signal very easy to demodulate. Really, all you have to do is rectify and low-pass filter the desired signal. This process is known as envelope detection, and this makes for essentially the simplest possible receiver. In fact, a lot of folks listening to this talk have probably built such a receiver. They're widely available as educational electronics kits. The alternative to large carrier AM is suppressed carrier AM. This scheme is shown in the lower right. Here we directly multiply the audio signal with carrier. As a result, the carrier can flip phase, and that happens whenever the audio flips phase. Now, this has the nice feature that no power is wasted in the carrier. That is, every ounce of power in the signal is used to send information. The price you pay for this is that, with the carrier gone, envelope detection is no longer possible. If you try envelope detecting the signal, well, then all those additional sign changes will just generate gibberish. Instead, you have to do something to sense the phase of the carrier so that you aren't confused by these additional sign changes. Another term for this is that you need a coherent receiver, which is much more complicated than a receiver that uses envelope detection. A technical improvement over DSB large carrier and DSB suppressed carrier is single-sideband, which you can think of as being AM with about 1/2 of the bandwidth. It's not possible in the scope of this lesson to explain entirely how this works, but there is a hint in the name. To go from double sideband modulation to single sideband modulation, you give up a sideband, which turns out to be okay because each sideband contains the same information. Obviously, this is great from a spectrum perspective. Single sideband sends the same amount of information in one-half the bandwidth. There are two popular single sideband AM schemes that you should probably know about. One is just called SSB, that's short for single sideband, and is used mostly for voice communication in the HF band. The other single sideband scheme is known as vestigial sideband, or VSB. In VSB, you include the carrier, as you do in large carrier double sideband AM, and it has the same trade-offs. VSB is probably best known as the modulation scheme for analog broadcast television in North America, which goes by the acronym NTSC. Since the transition to digital broadcast television in 2009, that new system known as ATSC, NTSC is less common, but there's still quite a bit of it out there in the VHF and UHF bands. Next up is frequency modulation, commonly abbreviated FM. In this scheme, the audio is used to vary the frequency of the carrier. The image at the bottom of the slide shows you what you get. The top waveform is the audio, and the bottom waveform is the modulated carrier. Perhaps the best known use of FM is in broadcast radio. Those signals around 100 megahertz or so that you can listen to on your car radio. However, FM is very common throughout the VHF and UHF bands, especially for land mobile radio. By land mobile radio, that is LMR, I mean primarily push-to-talk communications that are used by police, fire, taxi dispatch, and so on. Like any other modulation, FM entails some pros and cons. The big advantage of FM is a nice feature known as quieting. Quieting means that once you achieve a sufficient signal-noise ratio, the noise in the demodulated audio seems to disappear. This does not happen in AM. Obviously, quieting is highly desirable if you want to send high-quality audio, which is why it is used in broadcast FM. Also, quieting is very important if voice fidelity is essential, as in LMR communications between first responders like police and fire personnel. Now on to the digital modulations. Some common ones are shown in the table. Now, these are just the ones that involve combinations of amplitude and phase. There are others, not shown here, that use primarily frequency. Aside from which of the knobs are being turned, digital modulations can be sorted by how many symbols they use. That's indicated in the column labeled M. So, for example, a digital modulation that uses one symbol per bit has M equals 2, and each symbol conveys 1 bit. Similarly, a digital modulation that uses 4 symbols has M equals 4, and now each symbol conveys 2 bits, and so on. A very simple digital modulation is ook, as we introduced earlier, so let's take a look at that one first. The top row of the figure shows the symbols that we want to send. In this case, M equals 2, so symbols and bits are the same thing. The middle curve is the unmodulated carrier, and then the bottom curve is the modulated carrier. In digital modulations that manipulate amplitude and phase, it's often convenient to describe the modulation in terms of a constellation. This is simply a polar plot of the symbols. Each symbol has a unique amplitude and phase, and so appears as a single point on the plot. For example, for ook, the 0 symbol means amplitude is 0, so the 0 symbol appears at the origin of the constellation diagram. The 1 symbol, on the other hand, shows up as a non-zero value with a phase of 0. In this way, the constellation diagram is a useful tool for visualizing symbols in phase-amplitude digital modulations. A very common digital communication scheme is binary phase shift keying, abbreviated BPSK. BPSK is an M equals 2 scheme where the bits correspond to one of 2 opposite phases of the carrier. So, you can tell which bit is being sent by determining the phase of the carrier. And here's the constellation diagram for BPSK. Note that the BPSK signal always has constant magnitude, so the symbols are shown as having equal distance from the origin. And the symbols have opposite phase, so they're drawn as being on opposite sides of the origin. Once you see what's going on with ook and BPSK, is perhaps a little bit easier to understand other phase amplitude modulations that are commonly used, and here are a few. For example, QPSK is quadrature phase shift keying, which is similar to BPSK, except with m equals 4. That is, QPSK uses 4 symbols, so now you can send 2 bits at a time. QPSK represents symbols as phase shifts, just like BPSK, so the constellation diagram consists of 4 equally spaced symbols on a circle. Another phase amplitude digital modulation I'll mention is m equals 16 quadrature amplitude modulation, which is commonly called 16 QAM, or simply 16 QAM. In 16 QAM, you use both the amplitude and phase to define 16 symbols, as shown in the constellation diagram. With 16 symbols, you can send log base 2 of 16 symbols at a time. That is, you can send 4 bits at a time. Now, how big can M ultimately be, you might ask? Well, the answer is as big as you want, but there's a trade-off. And that trade-off is that performance in low signal-noise ratio conditions typically gets worse as M gets larger. Nevertheless, it is not uncommon to see 256 QAM, 1024 QAM, and beyond. Okay, let's take stock of what we've learned. First, modulation can be defined generally as the representation of information in a form suitable for transmission. Sinusoidal carrier modulation is a very broad category within the universe of all possible modulations. We talked about analog sinusoidal carrier modulations, including AM and variants thereof, and FM. We talked about phase amplitude digital modulations, including ook, BPSK, QPSK, and QAM. We talked about how these can be represented using constellation diagrams. I briefly mentioned, but I did not cover, the digital modulations in which frequency is also varied, but they're certainly out there as well. Remember that the thing that defines a digital modulation is the finite alphabet property. That is, you limit yourself to M carrier states, and that's all you're allowed to use. You get a performance benefit because the receiver knows in advance that's looking for one of M possible things, as opposed to a continuum of possibilities. Finally, we've just started to touch on the topic of bandwidth, but we haven't properly addressed it yet. That will be a topic for another lesson. However, you can anticipate that bandwidth will depend on the type of the modulation and also the rate at which information is sent. That concludes this talk on sinusoidal carrier modulation. Thanks for listening.